Hi everybody, it's Glenn again with number 10, standard reaction enthalpies. This is a Hess Law problem. I think you saw Hess Law in the last WebAssign and the second WebAssign. You have these chemical reactions and the enthalpies are known. Enthalpy meaning the heat that is required or the heat that is produced by the chemical reaction. Enthalpy is technically a form of energy that just includes heat. When the pressure is constant, such as when you do the chemical reaction in the open air, where the pressure is always going to be 1 atmosphere or whatever the air pressure is on that day, and when the pressure is constant, the enthalpy equals the heat, the Q. But when the pressure is not constant, such as when you do the chemical reaction in a sealed container, then the enthalpy is not just the heat, but it's a total of all the energy. So this goes beyond internal energy. But anyways, the important thing here is to notice that this equation can be made from these two equations. Let me show you. I'll write those two equations down. It has a delta H of 296.8 kilojoules. All right. Now, I'm going to make this equation from these two equations. Every time I adjust these two equations to fit this equation, I'm going to make that same adjustment to its enthalpy. So there are two S's in the reactants here. My S's are right here, but this is on the product side. I'm going to have to flip this so that the S's appear before the arrow, because that's where they appear in my target equation. When I flip it, I'm going to flip the sign of the enthalpy. That's necessary. But you see there are two S's here. So after I flip it, I still have some more work to do. Okay, I have flipped this. The sign is also flipped. But there are two S's that are necessary. I cannot get an S from any other place in these two equations. So I'm going to have to multiply this entire equation by 2. 2S, 2O2, 2SO2, and 2 times this also. All right, now I have 2 S's. Good. The next thing I need are 3 oxygens. I only have 2 oxygens here. Where can I get another one? Right there. But let's see. If I do that, well, let me try it, and then if I end up having to undo it, then I'll show you that too. So here I have 1 oxygen. Here I have 2 oxygens. I really need 3 oxygens, so I'm going to add this in here. And that's going to require me to use this also. All right. All right, so I've just added this in. I have not flipped it. I have not multiplied it by anything, so I keep the enthalpy as is. So if I were to add up these equations, I get 2S. Now watch closely here. I got 2S. I got 3 oxygens because there are 2 here and 1 here, so that's 3 oxygens. Oh, but I have this SO2. I don't want SO2. There's no SO2 anywhere in the target equation. How can I get rid of this? Well, If I can find SO2 somewhere on the product side, then I could cancel them in the same way as you did when you figured out net ionic equations in a previous module. So there are two SO2s here, the reactants, left of the arrow, but there are two SO2s here in the products to the right of the arrow. So these guys could cancel out. Lucky for me, I needed that to happen. Draw the arrow. I got 2 SO3. Is that what I wanted? Yes! The product side is just 2 SO3. So the enthalpy for this reaction, is equal to the sum of these enthalpies. So I'm going to multiply this by 2 and then add them together. 2 times 296.8, 2 times a negative, plus negative 197.8. Negative 791.4 is the answer. These are in the 10th place, both of them, so the answer needs to be in the 10th place also. I already forgot what it was. Negative 791.4. Okay? That's the answer. That was Hess Law, this method of adjusting equations and then adding them together, canceling out the things you don't need. This is all Hess's Law. Similar problem in number 11, but we don't need to use Hess's Law in quite the same way. In number 11, I've got these enthalpies of formation, you see. Let me tell you about formation. The enthalpy of formation is the enthalpy of the reaction for a special reaction called a formation reaction. This is the formation reaction for methane gas. The formation reaction is something that chemists made up. Methane gas is made of CH4. So the formation reaction is the let's say plus sign over here. The formation reaction is the reaction that forms this molecule in the state that you wanted it from its individual elements in the states where you find them under normal conditions. Normal conditions are room temperature and 1 atmosphere of pressure. So carbon is a solid at room temperature and 1 atmosphere of pressure. Hydrogen is a gas at room temperature and 1 atmosphere of pressure. So if I write the equation with hydrogen gas and carbon solid, if they make methane gas, this is the formation reaction for methane gas. By definition, since this is something that chemists made up, by definition this has to be 1 mole of methane gas. Because of this definition, sometimes in a formation reaction you might have fractions of moles. It could have been 1/2 H2. That would have gotten me a CH molecule. But in this case, I don't need fractions. But I just wanted to let you know that you could have fractions as coefficients in a formation reaction. So the heat of formation is the enthalpy of this reaction. This is a formation reaction, so the heat is given a special name, the enthalpy of formation. So for methane, it's negative 75. For carbon dioxide, it's negative 394. And for water, it's negative 286. If you can work this out with Hess's Law, but you don't have to because of the special nature of formation reactions. This is the target equation. I want to know what is the heat of reaction for this. All you have to do is add up all the products, heats of formation, and subtract from that all the sum of all the reactants, heats of formation. It's the products minus the reactants, folks. I've got 1 carbon dioxide. Okay, I'll do the products first. I've got 1 carbon dioxide at negative 394. I've got 2 waters at negative 286 each. I'm going to subtract from there a methane, which is negative 75, plus whatever else we've got here, oxygen. Now look at this. Oxygen is a pure element, O2. It's a gas. At room temperature and under regular atmospheric pressure, O2 is found as a gas in nature. So by definition, the chemists say that the heat of formation for O2 gas is 0. The reason is you don't need to do anything to it. It's already a pure element. It's already in its gas phase, which is what we usually find it as in nature. So the heat of formation of this is 0. All right? That's a special rule, folks. Pure elements in their usual states in nature have the heat of formation equal to 0. So I'll figure this problem out now. These were all kilojoules per mole. This is a typo. I should have put kilojoules per mole in here in the practice problem. So there's not going to be any problems with the units. Negative 394 plus 2 times negative 286. Minus negative 75. Negative 21,448 kilojoules. And this number, wait, this number is a little high, don't you think? 2 times 300 is 600. 600 plus 400 is 10,000. Yeah, this number is way too high. I'm going to recalculate that. Maybe I'll use parentheses this time. Minus a negative 75 is positive, is plus 75, the same thing. That's better. Negative 891. Okay, watch for the following trick, folks. It's very common for problems to give you joules per mole for one of these instead of kilojoules, in which case you have to convert that to kilojoules. They all have to be of the same units before you can add them up the way I just did here. All right, now this is the answer. Should it be negative? Negative enthalpy means heat got released usually. When you burn methane in oxygen, heat does get released. So yes, this should be negative. This is good. All right, now number 12. This corresponds to the first problem on your first WebAssign for this module. Energy of motion is called kinetic energy. That's all there is to it, folks. Just remember. Number 13. What's the final temperature of a gold nugget that starts at this temperature, loses this amount of heat, and then this is the specific heat capacity. So this is another one of those heat problems with the Q equation. We're going to be solving for the final temperature. This is easier than number 9 because water is not involved. Algebra is still necessary, but just a very little bit of algebra. The mass of the gold nugget is that. The heat capacity of the gold nugget is that. And the delta T is the final temperature minus the original temperature, which was 292 Kelvin. Now the Q, the heat, is negative 11,000 joules. It's negative because it loses that much heat. Okay? It is getting cold. If it already feels cold, that means it's absorbing heat. But this doesn't already feel cold. This is getting cold. So it's losing heat, not absorbing heat. So this is negative 11,000 joules. Why did I instantly convert this to joules instead of using kilojoules like they said? It's because joules are what the heat capacity is in. I can't have a problem in which I calculate kilojoules and joules at the same time. They always, I need the same units. Okay, so this was negative 11,000. Trying to fit that number in here. Negative 11,000 joules. All right, that's good. Okay, I have some algebra to do, so I'm going to remove all the units to make that easier for me. Now I'm going to solve for TF. $176.128. Times 292. 51,429. $40,429. That was positive. Okay, divide. So I have TF by itself on one side, but it's not completely by itself, so I divide both sides by the number to make it by itself. Those cancel. End up with TF equal to 229.5. This is a temperature, and the temperature previously has been given in Kelvin only to the ones place, no dots. So my answer is also going to be only to the ones place, no dots. Is 230 dot. Okay. I did say no dots, but what I meant was no numbers after the dot. I'm leaving a dot there because I want to make sure that you know that this 0 is significant. Okay? So that's the answer, 230 Kelvin. Does it make sense? The water used to be, not the water. There's no water here. This gold used to be 292 Kelvin. It was in a refrigeration unit, so the temperature dropped to 230 Kelvin. That does make sense. So that is great. That's the answer. See, it's very similar to number 9, but just easier. There's no water involved. Let me see if I can get number 14 done for you in the same video. Usually I have to stop and make a new video because the baby wants attention or something like that. You know what I mean? But in this case, the baby's taking a nap. So I might be able to do the rest of this in one go, I hope. How much energy is evolved for the formation of that much iron? Okay, so every time you run this reaction, you get this much energy out of it. But how many times are you going to run the reaction for this much iron? We've just done a similar problem earlier in this practice quiz in a different video. But I started that other problem with the energy. I'm going to do this in reverse so that you could see that you could do it both ways. The way the book does it is in reverse, in the following way. Start with the number they gave me. Change this to moles because I'm about to use that chemical equation. iron is 55.5 grams per mole, I believe it is. There's a periodic table given on the quiz, but I prefer this one sometimes. It's 55.845. Grams in 1 mole of iron. Why was that interesting? It was interesting because 2 moles of iron are involved in getting this much energy. I'm going to use that. 2 moles of iron are in the chemical equation, and this much energy is also associated with that chemical equation. So the grams of iron cancel, the moles of iron cancel. I only have kilojoules left. My memory ain't what she used to be, you know what I mean? $29.35. I've only got 3 significant figures there, so I can't even say 29.35. I really have to say 29.40. That's the answer, folks. Only 3 significant figures are allowed. Great. Last problem, number 15. Baby's still sleeping, so I can just keep on trucking here. I don't actually drive a truck. I think I would like to try trucking only if trucks became electric. Can't handle all that diesel fuel, the fumes and the fossil fuel dependence and all that. That has nothing to do with this problem. This problem is about Hess's law again. You see this DH, this just means delta H. Excuse me, I got this practice problem from elsewhere on the internet, and they didn't have a delta there for me, they just had this D. I'm going to be using Hess's law to add these equations up in some way to get this target equation. I've got CO2 here, but my CO2 is only available here. Oh, okay. There are a couple of typos. These R's really should be arrows. That's annoying, so I'm going to fix those typos right now while you're watching. Oh, wow. I can't fix them. Okay, sorry about that. I'll have to fix them after I make this video. Okay, so anyways, back to work. I got 5 CO2s here. Now I could get them from this CO2 or from this CO2. Let me write down these equations so that they're easier to look at. Are the states of matter going to be important here? This is gas, gas, gas. There are 2. The silicon things are solid. Silicon things are solid. Everything else is gas. SiO is a gas. It's also a gas here. Okay. Nobody is changing phases here, so I don't need to be worried about the phases. The enthalpy change here is 520.9. That's in kilojoules. All the enthalpies are in kilojoules. Good. Sometimes they try to trick you. The next one is 3SiO2. By the way, this is nitrous oxide. It is dinitrogen monoxide. It is the gas that they use at the dentist to sedate people or kids. Forgot that last compound. Si3N4. Silicon nitride. Okay. Oh, the enthalpy change? Negative 461.1. Silicon is a metalloid. That's kind of an interesting compound there. Right now, what was the target? The target was 5CO2 plus the silicon nitride makes silicon. Okay, let me start with those. 5CO2 and silicon nitride are in the reactants. Okay, I could get the CO2 from here. I could get the CO2 from here. But here I've got also the silicon nitride. I've got CO2 and silicon nitride, both in the same equation. I'm going to use this first because it's convenient. But my target has the CO2 and the silicon nitride in the reactants. This equation has them in the products. I need to flip it. So if I flip it, I'm also going to have to flip the sign of the enthalpy. That's going to be a positive 461.1 instead of a negative. So here we go. Take a different color. So I'm flipping that to 8CO2 plus Si3N4 produces 3 SiO2, 2 N2Os, 8 COs, and the enthalpy change is a positive 461.1. Now, there are a lot of products here. I don't need them all. I'm going to cancel some of them out and see what I need to cancel out. Looks like I need to cancel out, okay, I need 3 SiOs, 2 N2Os, and 5 COs. The rest I can cancel out. So I need 3 SiOs. Ooh. This is SiO2. It's not SiO. I need SiO. Let me get SiO. Here's SiO. Okay. How many SiOs did I need? I need 3 SiOs. So let me multiply this whole top equation by 3 and add it in. So I get 3 COs, 3 SiO2s, makes 3 SiOs, and 3 CO2s. And the enthalpy change is a positive 3 times 520.9. Now, just by doing that, I may have fixed other problems. So I've got 3 SiOs here. I've got 3 oxygens, but they're going to, I guess they're going to stay here. Huh. Now, this 3 SiO2, that's going to cancel with these 3 SiO2s because this is on the left of an arrow. This is on the right of the arrow. They cancel out. I've got 3 carbon monoxides here and 8 here. So 8 minus 3 is 5, so these 3 will cancel out, and I'll cancel just 3 of these 8 out over here. And it looks like I'm done. I've got 3 SiOs, 3 oxygens. Oh no, I have N2Os here. Let's see what I need. I need SiO, 3 SiO, 2 N2Os, and 5 carbon monoxides. I've got 3 SiOs, I've got 2 N2Os, and 5 carbon monoxides. What about these oxygens? I need a way to get rid of these oxygens. Did I miss something when I copied down this equation? That was where did this equation come from? This 8CO2 equation. Oh, it came from here. Okay. It was this one, I remember. So CO2 and silicon nitride, were they the only 2 products there? No. I mean, yes, 8CO2 and silicon nitride. There's no oxygen gas here anywhere. So this is impossible then. There must be a typo here. Okay, let me add these equations together. One of these equations is not balanced in the oxygen. All right, so I've got 8 CO2 and Si3N4 making 3 SiO plus 3 oxygens plus 2 N2O plus 5 CO. Where these oxygens, where did I get these guys? I got them from the CO equation. Oh, I see. I copied, there's no typo. I just copied this down wrong. This is not 3O2. It's 3CO2. So the products are SiO and CO2. SiO and CO2. Remember, I multiplied this whole thing by 3. There's a 3. Multiply this whole thing by 3. So this should be a CO2. Okay. This should be a, all right. Now that's CO2. This is 3 CO2. They're going to cancel with 3 of these 8 CO2s. So 8 minus 3 is 5. So I have 5 CO2s left and no CO2s here. It's like subtracting 3 CO2s on both sides of the equations. Gone here, and 8 minus 3 is 5 here. Now I can add them up. Sorry about that. It's an email. This is the silicon nitride. This is the 3 SiO. This is the 2 N2Os. This is the 5 COs. Is that the target equation? 5 silicon nitride, 3, 2, 5. 5 silicon nitride, 3, 2, 5. Yes, that is the target equation. So we'll add these up now. Positive numbers, that's interesting. Oops, sorry about that. 3 times 520.9. 2023.8. These are all in the tenths place, so the answer needs to be in the tenths place. And this is kilojoules. That's the answer, folks. 2023.8 kilojoules. And that is the last problem. That was a lot of work. Thank you for your hard work. I know that for you, because this week, at least, this material is new for you, it's doubly hard for you compared to how hard it is for me. So thank you very much for your hard work.